Principles of dynamic programming, memoization or iteration over subproblems. We now use the algorithm for the weighted interval scheduling problem developed in the previous section to summarize the basic principles of dynamic programming and also to offer a different perspective that will be fundamental to the rest of our chapter, iterating over subproblems rather than computing solutions recursively. In the previous section, we developed a polynomial time solution to the weighted interval scheduling problem by first designing an exponential time recursive algorithm and then converting it by memoization to an efficient recursive algorithm that consulted a global array M of optimal solutions to subproblems. To really understand what is going on here, however, it helps to formulate an essentially equivalent version of the algorithm. It is this new formulation that most explicitly captures the essence of the dynamic programming technique, and it will serve as a general template for the algorithms we developed in later sections. Designing the algorithm. The key to the efficient algorithm is really the array M. It encodes the notion that we are using the value of optimal solutions to the subproblems on intervals between 1, 2, 3, and until j for each j. And it uses 6.1 to define the value of M with index j based on values that come earlier in the array. Once we have the array M, the problem is solved. Mn contains the value of the optimal solution on the full instance, and the find solution can be used to trace back through M efficient and return an optimal solution itself. The point to realize then is that we can directly compute the entries in M by an iterative algorithm, rather than using memoized recursion. We just start with M 0 equals to 0 and keep incrementing j. Each time we need to determine a value mj. The answer is provided by 6.1. The algorithm looks as follows. Iterative compute OPT. M0 is equals to 0, and for j starting from 1 to 3 until n, we let mj equals to the maxima chosen between vj plus m of p of j or m of j minus 1 and 4. Analyzing the algorithm. By exact analogy with the proof of 6.3, we can prove by induction on j that this algorithm writes OPT of j in array entry m of j. 6.1 provides the induction step. Also, as before, we can pass the field in array m to find solution to get an optimal solution in addition to the value. Finally, the running time of iterative compute OPT is clearly big O of n, since it explicitly runs for n iterations and spends constant time in each. An example of the execution of iterative compute OPT is depicted in figure 6.5. In each iteration, the algorithm fills in one additional entry of the array M by comparing the values of bj plus m of bj to the value of m of j minus 1. A basic outline of dynamic programming. This then provides a second efficient algorithm to solve the weighted interval scheduling problem. The two approaches clearly have a great deal of conceptual overlap since they both grow from the insight contained in the recurrence 6.1. For the remainder of the chapter, we will develop the dynamic programming algorithms using the second type of approach, iterative building up of subproblems, because the algorithms are often simpler to express this way, but In each case that we consider, there is an equivalent way to formulate the algorithm as a memoid recursion. Most crucially, the bulk of our discussion about the particular problem of selecting intervals can be cast more generally as a rough template for designing dynamic programming algorithms. To set about developing an algorithm based on dynamic programming, one needs a collection of subproblems derived from the original problem that satisfies a few basic properties. 1. There are only a polynomial number of subproblems. 2. The solution to the original problem can be easily computed from the solutions to the subproblems. For example, the original problem may actually be one of the subproblems. 3. There is a natural ordering on subproblems from smallest to largest, together with an easy-to-compute recurrence, as in 6.1 and 6.2, that allows one to determine the solution to a subproblem from the solutions to some number of smaller subproblems. Naturally, there are informal guidelines. In particular, the notion of smaller in Part 3 will depend on the type of recurrence one has. We will see that it is sometimes easier to start the process of designing such an algorithm by formulating a set of subproblems that looks natural and then figuring out a recurrence that links them together. But often, as happened in the case of weighted interval scheduling, it can be useful to first define a recurrence by reasoning about the structure of an optimal solution, and then determine which subproblems will be necessary to unwind the recurrence. This chicken and egg relationship between subproblems and recurrence is a subtle issue underlying dynamic programming. Underlying dynamic programming, it's never clear that a collection of subproblems will be useful until one finds a recurrence linking them together, but it can be difficult to think about recurrences in the absence of the smaller subproblems that they build on. In subsequent sections, we will develop further practice in managing this design trade-off.